Okay, hi guys, welcome. Let's begin. We have a pretty exciting lesson. This is going to be the essence of calculus. So you've heard that word, as Mariam's just told us. What does it mean? Today you're going to find out. So we just have to do a quick recap. You'll see at the bottom of our page on Introduction to Limits, that's what we did last, 14C. Today we would be doing 14D.1. But we're going to just work through the work booklet here. I've put a number of questions and exercises in here that I want us to focus on first. And it's really good, it's working in our favour that we get those sort of two lessons back to back on Thursday, Friday, because it means tomorrow we're going to be really able to cement what we're going to learn today. So this takes us back to last semester when we're talking about not only function notation, but composite functions. So if this is f of x, we know f of 1 means we put the number 1 everywhere there's an x. So let's go through and evaluate these four that we've got. So f of 1 is going to be 1 squared plus 2 times 1 plus 3. So that's going to be 1 plus 2 plus 3. That's going to be 6. F of h is where we're going to put a h everywhere the x is. So we're going to have h squared plus 2h plus 3. And we can't simplify it more than that because there's no like terms along there. Okay, f of x plus 2, that's where we're going to put this whole linear equation everywhere there's an x. So we would have x plus 2 squared plus 2 times x plus 2 plus 3. Alright, so I've put everything in here, everywhere there's an x, there and there. Okay, and then we would need to expand and collect like terms. So let's do that. That's a skill we're going to assume that we've got here. Here, this is perfect square expansion. That's going to expand to x squared plus 4x plus 4 plus 2x plus 4 plus 3. Okay, any questions about that? Very good. And then all along here, we've got a number of like terms. We've got 4x and 2x. And then we've got 4, 4, and 3. So this would collect to x squared plus 6x plus 11. Okay. F of x plus h. So I'm going to do that one here. F of x plus h, a little bit ambitious if we're going to be getting all these together. So this time we're going to put x plus h everywhere there's an x. So that's going to give us x plus h squared plus 2 times x plus h, and then plus 3. We've substituted x plus h everywhere there's an x. And now let's perform that expansion and collect any like terms. So here we're going to have x squared plus 2xh plus h squared. Okay, that's perfect square expansion. A squared plus 2ab plus b squared plus 2x plus 2h plus 3. Are there any like terms? No. Okay. Like terms have to have the same exponent and the same variable. Here you can see we've got, this is just x squared, there's no other x squared term. Here we've got 2 times x times h. So there's no other xh term. We have an x term, we have a h term, but we don't have anywhere an xh term. So that's as far as we can expand that one. Fantastic. So just a bit of a recap there. Let's jump over to the next part. This is where we're getting into it. So I'm going to rub that off. We have a quadratic. F of x is x squared. Step 1. Draw a chord from x is 2 to x is 3. Okay, so if this is our equation, x is 2, it's about here. You've got it drawn in front of you. And x is 3 is here. And a chord is going to be a line that joins those two together. Hence, find the average rate of change between 2 and 3. Okay, remember, average rate of change in ERAC is y2 take y1 on x2 take x1. So we've got these x values. We know the x values at this point. That's 2 and that's 3. What's the y value? Well, the equation of this curve is y equals x squared. tells us at the top, consider y equals x squared. So that means, given the x value is 2, the y value is going to be 2 squared, which is 4. And over here, the x value is 3, the y value is going to be 3 squared, which is 9. Now we've got 2 sets of coordinates, we can go through and find the slope. Okay? Give you 30 seconds to do that. Find the average rate of change, so part 1. Go ahead and find the slope. And so we'll have 9 take 4, on 3 take 2, 5 on 1. Okay, so we have an average slope of 5 over this interval. y2 take y1 and x2 take x1. Very good, all wonderful. That's part 1 complete. Part 2, let us find the instantaneous rate of change at x is 2. So remember, average rate of change over an interval. Instantaneous rate of change means occurring at that point. Now, how do we find the rate of change at that point? Well, we can draw a tangent. I didn't bring my cool ruler today, but we can draw a tangent. And so a tangent is going to be a line that is parallel to the curve at that point. So if we think, what is the slope of the curve at that point? We need a line that's parallel and touches it. Okay, so that the slope of this line is the same as the slope of the curve at that point. So use a ruler or something straight, or maybe you're really good at drawing freehand lines. So we get the same curve, and then we want to go, what's the slope of this line? Because that's going to give to us an indication, albeit an approximation, an indication of the slope of the curve at that point. So you can go ahead and do that, and we can compare our results. We'll give you a couple of minutes to do that one. Hit record. Okay, so we did instantaneous rate of change at x is 2. Now, what we're going to do is we're going to use a really clever technique. So that's one way we could do it graphically, but it's subject to a lot of error, isn't it? You know, if people have drawn a tangent just slightly differently, then their slopes are going to be different. So we can use a really cool mathematical technique. What we're going to do is we're going to have point P. We want to know the rate of change at point P, isn't it? That's when x is 2. We want to know what is the slope at that point. And so what we can do is we can imagine point M. Okay? So we're going to zoom in on the curve and we're going to say point M is really close to point P. In fact, point M, we're going to start with, point M has a slope of 2.1. Okay? Has an x coordinate of 2.1. So if the x value is 2.1, the y value is going to be 2.1 squared. So that's going to be, what's that, 4.01, I think. Better check. All right, and so we're going to get this x value and this y value. And now we're going to say if we move M closer and closer and closer to point P, we can move it so close that eventually it's at point P. That's what we'll do in a moment. But let's begin by using this as point M, 4.41, sorry. So when x is 2.1, we have y is 4.41. And so then we're going to say, well, what is the slope of Pm when m is at 2.1? Okay, so now we're saying, what's the slope of this chord now that we've moved m? Before it was at 3, now we've moved it to 2.1. What's the slope of the chord now? Okay, same technique. y2 take y1 on x2 take x1. So let's perform that. We're going to have 4.41 take 4 on 2.1 take 2. 0.41 on 0.1. We've got a slope of 4.1. Okay, so we moved m's pretty close to P, 2.1, and we found that had a slope of 4.1. So based on this, at this point, you know, Brad's a bit closer than most of you guys. Brad got 4.16. Base here, we've got a slope of 4.1. What about if we move m even closer? In fact, let's move it to 2.01. Okay, so now m, rather than being there, we're going to crank it right down to here. It's even closer. it's closer, so that its slope now, its x-coordinate now is 2.01. 2.01 squared, 4.0401. Okay, let's perform the same technique. We want to know what is the slope of PM now that M is closer to P. So we'll go through and do that. We've got 4.0401. Y2 take Y1. On X2 take X1. We're left with 0.401 and 4.01. So look what happened to the slope when we moved M closer to point P. Okay? So before we saw when we had X at 2.1, the slope was 4.1. Now we've moved it closer, it's 4.01. What do we think is going to happen when we move it even closer? We're going to move it so close, all right, that it's pretty much they're pretty much next to each other. But you can imagine if you zoom in on it, like on either Google Earth or you zoom in on the surface of the Earth, it appears flat to us. Okay, if you zoom in enough, it will appear like a straight line. So we're saying, what is the slope of that straight line? So if we use 2.001, let's do that. 2.001. Square it, we've got 4.004001. Okay, now let's find the slope when it's even closer. We're going to have 4.004001. Okay, it's going to be 0.004001 on 0.001. Which will be 4.001. Okay, so what's the pattern we can see here? What's happening as M gets closer and closer to P? What's happening to the slope of PM? It's getting closer and closer and closer to 4. Okay, so that was a very good calculation by you guys to get 4. So now then, okay, now that we can do that, let's turn the page over, part 4, make a conjecture, okay? So we've got really good evidence from here to infer, if we've gone from 4.1 to 4.01 to 4.001, that the slope at P, if we can imagine M is infinitely close to P, in fact it is so close to P, that it's almost right next to it, what the slope of PM is going to be. So we'll say, make a conjecture. So our conjecture, let's talk about how we're going to write this. I might rub this out because I don't think we need that anymore. So we're going to write, it is conjectured that as M approaches P, as M gets closer to point P, the slope of PM approaches 4. Okay, as M's getting closer and closer and closer to P, the slope of PM, that chord, is getting closer and closer to 4. And what evidence do we have? From that table that we just performed when we started to move it closer and closer. Okay, so conjecture, that's just a mathematical hypothesis. And that's all it is at this stage until we can prove it. And we can actually use a really clever technique to prove that the slope is 4. We can prove this is true. So we've got good inductive evidence. Now let's prove it deductively. So what we're going to imagine now is that we're still at that point P, and we've got point M, but point M does not have an x value of 2.01 or 2.001. It has an x value of 2 plus h, where h is approaching 0, where h is pretty much 0. It's so close to 0 that there's hardly any difference between them. Okay, remember what's the function? Y equals x squared. If we have a value of 2 plus h, the x value is 2 plus h, what's the y value going to be? It's going to be that whole x value squared. Okay, so we've got our x value, we've got our y value, we've got everything we need to calculate the slope of this chord where m is so close to p that the difference between them is almost nothing, where it's almost zero. Okay? So for p is at 2 and n is at 2 plus h, which is like 0.00, like an infinite number of zeros and then a number 1 at the end. It's so close to it. This is going to be the y value, okay? Because the y value is the x value squared. If this is our x value, we square it, that's generating our y value. We're ready to find the slope of Pm. The slope of Pm is going to be y2 take y1. 2 plus h squared take 4. y2 take y1 on x2 take x1. Okay, let's evaluate this a bit. So we're going to have perfect square expansion here. We're going to have 4 plus 4h plus h squared take 4. Okay, so there, a squared plus 2ab plus b squared. That's that part. And we have take 4, that's hanging out there. 2 plus h take 2 just simplifies to h at the bottom. Now we have, at the top, with some like terms we can collect, we've got 4 and minus 4, so we can cancel those. And what are we left with? We've got 4h plus h squared at the top, on top of h at the bottom. We can factorize h and cancel it. So we could write this as h times 4 plus h on top of h. We've got h at the top, h at the bottom as a product that can cancel. And so we're left with 4 plus h. Okay, once we've processed this, what did we say? H is really close to it. We're performing the slope here, we're expanding, collecting like terms. This is what we've got when we've processed it. But what is h? H is approaching 0. So if this approaches 0, we have a slope of 4 as it gets closer and closer and closer to it. Beautiful. That is amazing. Okay, hence determine the slope. So that's what we did there. Okay, we're on to number 7. Okay, so we're going to develop some more conjectures here. So now we're saying, okay, that's the slope at point P. What would happen if we move point P around the place? And we say, what about if point P, rather than being at 2 and 4, we're going to say point P is, now it's going to be at x is 1. Okay, so if the x value is 1, the y value is going to be 1 squared, which is 1. So we have 1, 1. And we're going to repeat this same process that we did there. We're going to have point M, which is infinitely close to it. Okay, point M is going to be x value 1 plus h. Okay, 1 plus h, where h is approaching 0. Okay, it's infinitely close to it. The y value is just the x value squared. Okay, that's the equation that we're talking about here. Y is x squared. Okay, and now we're asked to find, well, what's the slope of Pm if we move P to this point here? When at this point, what's the slope there? Because obviously, like if you think of the curve, the slope here is different from the slope there. Okay, here it's going to be steeper, here it's going to be less steep. So our question is, well, how steep is it here? And we're going to hop around a bit. And we're going to see if we can make another conjecture about the slope of different values of x. So let's go through this one together, and then I'll get you started on the rest of the part there by yourself. So what you're going to perform here, we need to find the slope of Pm when P is at x is 1. Well, slope is y2 take y1 on x2 take x1. So let's go ahead and do that. We're going to have 1 plus h squared take 1 on 1 plus h take 1. Okay, we need to expand and collect like terms. Okay, so watch what we do again. With perfect square expansion, we're going to have 1 squared plus 2 times 1 times h, so plus 2h, plus h squared, take 1, and then at the bottom we've got h. Okay, 1 and 1 will cancel. we're left with 2h plus h squared on h. We can factorize h from the top and cancel it at the bottom. So we're left with 2 plus h. So what have we done again? We're saying it's infinitely close. H is pretty much 0. Here's the slope formula. We've processed it. We've got 2 plus h. What is h? It's pretty much 0. H is going to 0. And so the slope at when x is 1 is 2. Okay, so we're ready to fill in this table here. So I've filled in the first one for you. Let me draw it up so I can. I've got it up on the keyboard here, but I'm drawing it up again. So we've got when x is 1, y is 1. Okay, we saw that. When x is 1 plus h, y is, in brackets, 1 plus h squared. And we performed that expansion. And then we saw, when we do that, the slope of PM, okay, at x is 1, the slope of PM is 2. So we've done that one. On the previous page, we did the slope at x is 2, didn't we? That's what we did on the previous page. And we found here the slope was 4. Okay, so we've already performed the second row here. We can just fill that in based on what we saw on the previous page. So that was our slope, 2 plus h squared. We had a y value of 2 squared, 4. Okay, so I want you to fill in the next 2 rows. There we go. Okay, so excellent. So we're starting to notice a pattern. I think some of us, the expansion can be a bit tricky because there is a lot going on. So don't be disheartened. All right, this is calculus, isn't it? You know. Okay, so what we've got is we've got this sort of table we've drawn up. We've got these x values, we've got these y values, and then we've got the slope at these points. So we're saying point P is at x is 1, point P is at x is 2, point P is at x is 3. And look at the slope, okay? And we can start to see some patterns, isn't it? You know, if x is 1, we've got slope is 2. If x is 2, slope is 4. If x is 3, slope is 6. So then we're asked, okay, over the page, from the table, what do you expect the slope to be when x is 5, when x is 6, and when x is 7? Okay, so the relationship hopefully we're picking up is that it's just 2, whatever the x value is, you multiply it by 2, and that's going to give you the slope. So we've got when x is 5, slope is 10, when x is 6, 12, when x is 7, 14. Okay, so we could perform this process forever, okay, for all these different values of x. All right? But we can actually prove it for any value of x. All right, and that's what's going to be very useful for us. So we have part 9 here. Make a conjecture about the slope with coordinate p for any value of x. So I'm saying coordinate p could be anywhere on this curve. Okay, it could be when x is positive 1,000, could be when x is 0.2. Anywhere on the curve, x represents any value on this curve. So if point P is x, then the y value is going to be x squared. And we saw, our pattern that we notice is that whatever the x value is, the slope is just 2 times the x value. Okay? So if we're talking about an x value of x, okay, when P is at x and x squared, the slope is, this is our conjecture, 2 times the x value. What is 2 times x? 2x. Okay, for any value of x. So we could anticipate when x is 1,000, the slope is 2,000. When x is 0.5, the slope would be 1. Okay, that's what we're saying here. We're saying for any value of x, when p is anywhere on this curve, the slope is always 2 times whatever the x value is. That's going to be our conjecture. And we've got good evidence from here, don't we? X is 1, the slope is 2 times it. When x is 2, the slope is 2 times it. When x is 3, 6. Okay, we've got good evidence. All right, so let's prove it. Let's prove that this conjecture, let's prove this is the case. So the way we're going to do that is we're going to have point P, and we're going to have point M again. Okay, and again, we're going to have M is really, really close to point P. In fact, it is x plus h close, where h is approaching 0. So if we have x plus h, the y value will be x plus h squared. And then we're just finding the slope of Pm for these values of x. y2 take y1 on x2 take x1. Let's perform that. We've got x plus h squared, y2 take y1 on top of x2 take x1. Okay, we're going to expand, collect like terms, factorize that h, and cancel down. So my perfect square expansion first, x squared plus 2xh plus h squared. A squared plus 2ab plus b squared. Take x squared, and at the bottom we've got x take x, so that's going to leave us with h. At the top we've got x squared take x squared, so that'll cancel. So what do we got? We've got 2xh plus h squared on h. And already if we've been doing this pattern enough times, we can see what we have to do. Factorize h. We cancel it. And so we're left with 2x plus h. And h is approaching 0. That's what we stipulated. M is really close to it. Pretty much there. Pretty much 0. And so if h is approaching 0, then as m gets closer and closer to point P, the slope approaches 2x. So we have proved that for this equation, it's true for this equation, it's going to be different for others, for the equation y equals x squared, for any value of x, the slope is going to be 2 slope function. Okay, and that is what tells us the slope for any value of x. Okay. Any questions about that procedure there? Okay, because we did it for x squared, right? But we can imagine it for any curve. I'm just sitting around my own trouble. Okay, so this is where we're going to develop a formula. And if you're a bit lost, don't worry, because from now on we're just going to be applying the formula. So let's turn over to the derivative function and first principles. So we can imagine any curve. Okay, it could be a cubic, could be a quartic, could be a sine function, could be anything. Okay, we've got any function. And we can imagine point P being anywhere on this function. Point P has an x value of x. Okay, and the function we're talking about is some function of x. Any function, anything you want it to be. So if this is the x value, then the y value is just going to be f of x. All right, whatever the x value is, you put it into f of x to get the y value. And then we're going to say, and now we've got point n, which is infinitely close to it. In fact, it's x plus h close to it as h approaches 0. So if we have an x value of x plus h, well, the way you would find the y value is plug that into here, isn't it? You'd have f of x plus h. Okay, and so then for any function, doesn't matter what it is, the instantaneous rate of change, we learned this notation yesterday, the limit as h approaches 0, that's what we've been doing, we've been applying limits here, of y2 take y1 on x2 on x2, x plus h, take x1, is going to be the slope of any function. Okay? This is what we call first principles. Okay, and this is our first introduction to calculus. So what is calculus then? Calculus is about the instantaneous rate of change. It's the slope of a curve at any point in time. And we're going to use this procedure here, developed by both Newton and Leibniz, contemporaneously. We're going to use this procedure here to find the slope for lots of different functions. Okay, and you might notice this can actually simplify at the bottom. Okay, you've got x plus h take x. this is it in its simplest form. The slope for any function is f of x plus h. Take f of x on top of h. Okay. Now we introduce you to some notation up there as well. Have a look up on my computer or on your books there. We've got the function, okay, and words we use to describe it, or the notation we use is f of x and y. We could say f of x equals y. And whenever you put an x value into the function, it's going to tell you the corresponding y value. You say x is 5, what's the y value when x is 5? It's going to tell you. What we've learned today though is the slope function. Okay, the slope function or the derivative function. Okay, so there's some cool words that we're going to be using. We're going to use both of those. They mean the same thing. And that's going to be a function. We represent that as either f dash and then in brackets x, or as dy on dx. Okay, so we're going to have here f dash of x, the slope function, is equal to, that's the procedure we perform. That's our formula we're talking about. And when you put an x value into the slope function, it's going to tell you for any function, for any curve, how steep it is at one exact point in time. Okay, so we've got our formula. We've filled in the booklet a bit. We've seen how we develop it. It's 246. We're going to do a few examples using the formula. Okay, so if you sort of found that challenging, doesn't matter. This is where we're going to use the knowledge that we've got. So I've got 3 examples for us. Okay, you notice it's pretty similar to x squared. This time, it is x squared plus 3x. Okay, so we're going to use the function x squared plus 3x. That's f of x, isn't it? That's the function, and we want to find the slope function for x squared plus 3x. We want to find the derivative function. We're going to use this formula here. We want to find f dash of x. Okay, so f dash of x equals the limit as h approaches 0. This is notation that we need to use throughout our whole process that we're going to perform. F of x plus h. Okay, so we're plus h. Okay, we've got f of x plus h. Okay, that's that part there. Take away f of x. So we take, I'm going to put this in brackets, by the way. So we've got f of x plus h, that's that part. Take away f of x. I'm also going to put this in brackets, and I'm going to really encourage you to do the same always. Okay, so boys up front, boys are notorious for this slip up, because that negative needs to apply to this term and this term. If you don't put brackets there, you've got minus x squared plus 3x. Okay, that's a stuff up. Brackets, so that the negative applies to both of these terms. You're subtracting all of f of x. So what have we got? We've got f of x plus h. Take f of x, okay, f of x plus h, take f of x on top of h. Got to expand, collect like terms. Let's do that. Okay, so it's going to be a long thing. It's going to be long. We just focus on each part at a time. X plus h squared, perfect square expansion. X squared plus 2xh plus h squared. Okay, that's what that part expands to. Here, that 3 just distributes. So I've got plus 3x plus 3h. Okay? And then here, that negative just distributes, doesn't it? So we're going to have take x squared and take 3x, all on top of h. Okay, let's look for some like terms along there. Here we've got x squared, and here we've got minus x squared. That's going to cancel. Here we've got 3x, and over here we've got minus 3x. That's going to cancel. Okay, so let's restate what we're left with once we've done all that cancelling. We're going to have 2xh plus h squared plus 3h on top of h. Okay, we're starting to recognise a bit of a process here, and I'll write up some steps for us. Okay, when we're at this step, this is a way for us to check if we're going to get the right answer. Okay, throughout this whole thing, there are ways of checking if you're on the right track. This is a crucial step. When we're here, the next thing we want to do is factorize h and cancel it. We can only factorize h if every single term has a h in it. Okay, so if, for instance, we've got this minus 3x hanging out here, it means we've done something wrong because it doesn't have a h in it. Okay, so that can be a backtrack, fix it up. Here, look, we've got h there, we've got h there, we've got h there. We can factorize h out the front. So I'll go sideways. We've got the limit as h approaches 0. We're going to have h times, I'm pulling h out the front. What am I left with if I pull h out the front? We're going to have 2x plus h plus 3. Okay, plus h. Okay, we've got f of x plus h. Okay, that's that part there. Take away f of x. So we need take, I'm going to put this in brackets, by the way. So we've got f of x plus h, that's that part. Take away f of x. I'm also going to put this in brackets, and I'm going to really encourage you to do the same always. Okay, so boys up front, boys are notorious for this slip up, because that negative needs to apply to this term and this term. If you don't put brackets there, you've got minus x squared plus 3x. Okay, that's a stuff up. Brackets, so that the negative applies to both of these terms. You're subtracting all of f of x. So what have we got? We've got f of x plus h. Take f of x, okay, f of x plus h, take f of x on top of h. We've got to expand, collect like terms. Let's do that. Okay, so it's going to be a long thing. It's going to be long. We just focus on each part at a time. X plus h squared, perfect square expansion. X squared plus 2xh plus h squared. Okay, that's what that part expands to. Here, that 3 just distributes. So we've got plus 3x plus 3h. Okay? And then here, that negative just distributes, doesn't it? So we're going to have take x squared and take 3x, all on top of h. Okay, let's look for some like terms along there. Here we've got x squared, and here we've got minus x squared. That's going to cancel. Here we've got 3x, and over here we've got minus 3x. That's going to cancel. Okay, so let's restate what we're left with once we've done all that cancelling. We're going to have 2xh plus h squared plus 3h on top of h. Okay, we're starting to recognise a bit of a process here, and I'll write up some steps for us. Okay, when we're at this step, this is a way for us to check if we're going to get the right answer. Okay, throughout this whole thing, there are ways of checking if you're on the right track. This is a crucial step. When we're here, Now, the next thing we want to do is factorize H and cancel it. We can only factorize H if every single term has a H in it. Okay, so if, for instance, we've got this minus 3x hanging out here, it means we've done something wrong because it doesn't have a H in it. Okay, so that can be a backtrack, fix it up. Here, look, we've got H there, we've got H there, we've got H there. We can factorize H out the front. So I'll go sideways. We've got the limit as H approaches 0. We're going to have H times, I'm pulling H out the front. What am I left with if I pull H out the front? We're going to have 2x plus H plus 3. Okay, H